All right, welcome everyone to my 13.4 pre-class video. This section is all about projectile motion, and the way that I'm going to end this video is by doing a problem very similar to homework 5. And so please stick around for that, and I'll show you again a problem that's kind of inspired by this and very close to it, and we'll go over how to solve that here at the end. But before we get into that, I usually like to start these things with a bit of an administrative announcement or some things that you may not have known about. And so earlier today, right, I sent an email basically just introducing us to week 4 and all that good stuff. And in there, right, I mentioned that the exam is coming up, right? We have less than 2 weeks away. And so I've kind of, when I posted this on D2L, I split it up into kind of the standard to-do list for week 4, and then also a little bit of information about exam 1. And so this has kind of the standard stuff. A lot of this is already mentioned in the syllabus, so it shouldn't be wildly interesting or surprising or anything like that. I do give some, personal thoughts or ideas of ways that I've found success in studying throughout the years, but I mean, certainly everyone's different and you need to find what works for you. But the biggest thing here is just in this link, right? Here are some tips for studying for the midterm exam. And this is in the email as well as here, right? But if you go ahead and you click on this, it takes you to a fairly decent page of some study ideas, and then that same kind of general study advice that I had sent out now a couple times here. So we have a couple of opportunities, right, for review. And again, this is still a ways out, but you should be thinking about it now. I know one common question, I've already seen it on Piazza, and so I know that there are people thinking about this, is kind of what kind of review opportunities do we have, right? And so Wednesday's class before the exam, remember the exam is on Thursday, October 1st. So the Wednesday's class before the exam is a review session. And so the instructors are going to provide some problems that they want to focus on and all that good stuff. Also, the Thursday's recitation before the exam, right? The exam is at 8 o'clock at night. All the recitations are before that. Again, that 8 o'clock is Eastern Daylight Time. So if you're in a different time zone and whatnot, please adjust that accordingly. We also have, right, I have office hours twice a week. There's a lot of MLC shifts. Other instructors have office hours, right? I went ahead and I included a link to this the Math 234 teaching roster, and kind of it has all the MLC and office hour shifts and all that sort of stuff. So there's lots of opportunity for you to come and ask questions as well, instead of just getting, seeing more problems and whatnot. Here's something nice. This has come up, excuse me. I have something in my throat, it seems. This has come up a little bit on Piazza already. People have asked about a formula sheet. There is going to be a formula sheet. Let me go ahead and just click on this one. I'll open it in a new tab here. This is what the exam 1 formula sheet looks like. And as you go through this, right, there's going to be a lot of stuff that looks quite familiar now, right? So vectors in space. So this is a lot of the chapter 12 stuff. You get some of the unit vectors. You get the length of the vector or the magnitude, dot product, cross product, vector projection. But for instance, notice here, and this is reiterated in several places, right, that these formula sheets are not all inclusive, right? And so you need to know, right, what is on here, and that's kind of why I'm bringing this up now, and what's not, right? There are going to be other techniques, there's going to be other information, right, that you should know, or at least be able to build from these things. So for instance, right, scalar projection's not here, right? We have vector projection, but scalar projection isn't here. However, right, we should know how to build maybe the scalar projection part from this, right? It's just kind of like the magnitude, or if you just move one of these magnitudes of u over here, and then take that unit vector off, right? That u dot v divided by the magnitude of u, that's just the scalar projection. So many of these things you can build kind of the missing pieces from this. We can see here that we get a line parallel to v, a plane normal to n, right? There's quite a lot of information is given here. This will come up, especially more later on. I can't think of too many cases. I guess maybe, we've started taking derivatives or integrating here in chapter 13 a little bit. So if you needed to integrate, for instance, 2 sine x cosine x for whatever reason, or probably there's going to be t's there instead of x's, that maybe we don't know how to do this, right? Because this is a product of things, but we could go ahead and exchange that for sine of 2x or 2t. So yeah, those are some kind of, nice kind of, not really calculus things, but just geometry and trig things that can come up. Later on, when we're parameterizing surfaces, these transformations will make more sense and will be more useful. Arc length we haven't seen yet, and we have seen unit tangent vector. So that's just kind of a quick overview about the formula sheet, what's on there. And of course, you'll identify a fair amount that's not on there, right? So these are still things that you should put to memory and everything. Okay. The last bit here that I'll mention, right, is I would recommend that you review your quizzes, right? So we've taken the time and the effort to write in feedback, right? And basically like the ideas of solutions into the quiz problems. And you can also, right, go and view your old quizzes, see what you got right, see what you got wrong. And this is just what I say here, right? If we like those questions once for the quizzes, it's very possible that we will like them again and that we could reuse them for the exams. Plus, they're already coded in D2L, so we wouldn't even have to spend a lot of time recoding things or anything like that. Now, of course, right, when people hear that, they I don't know, they think, oh, maybe they're all going to be quiz questions, and that's certainly not going to be the case, right? So this does not guarantee that most of the questions will be repeats from the quizzes, right? There certainly will be new questions, and so you need to prepare for that as well. Certainly, you should review your WebWork homework, and the textbook has a great conceptual review at the end of each chapter, as well as some true-false questions. And so I would recommend taking a look at those as well. All right, with that, why don't we go ahead and go over, and like I said, I wanted to do a problem that was quite similar to this. I'm going to stop sharing with my desktop here. I'm going to start sharing with my iPad. So this will just take a second to get this all transitioned over. I have to hit start broadcast, and then it should be coming up. All right. So here, find the velocity and the position vectors of a particle that has the given conditions. So we're given that this here, we have an acceleration at all time, right? It just says a of t. We have velocity and we have position, right? And so this is just velocity at time 0, and this is just position at time 1. And we want to figure out, our goal here is we'd like to find the velocity vectors, so maybe v of t in this case, and we want to find the position vector, so maybe r of t. So the full-on vector here, not just at a specific time, but for all time. Right? So that's going to be our goal in order to win this. So really, this is combining two things. This is combining our Calc 1 knowledge, right? We should know how to go from acceleration to velocity and from velocity to position. This is just going to be with antiderivatives, right? So this is kind of some classic Calc 1 stuff. Plus from 13.2, we learned how to take antiderivatives of vector functions, right? And we learned that basically you just do it to each piece. So those are the two things that we're going to be combining in order to solve this problem here. All right, so let's go ahead and start off. If I wanted to calculate out v of t, again, from our Calc 1, we know that we're going to be integrating acceleration with respect to time. Now, these things are all vectors, right? And that's what makes it a Calc 3 problem rather than a Calc 1 problem. So we're going to be integrating, and this is the vector 1 to 0 with respect to time. And of course, when we integrate this, well, this is a constant vector, and there's a couple of ways that you can think about this. One is that, right, you just integrate each piece. So if I integrate 1, this becomes t, 2t, and 0t, aka just 0. So you could do it like this, or you could say, hey, this is a constant vector. And so some people may look at this and say, this is going to be this constant. And when I integrate a constant, well, you get a t out in front, right? That's the antiderivative. And notice, of course, if you distribute that t to each piece, you end up with the same result. So all roads, I mean, if you're doing things right, all roads lead to this answer here. But a big thing about indefinite integrals, right, is that they can't really detect constants so well, right? You could add any old constant here, and this would still be a perfectly good antiderivative. And so when we integrate these things, as we saw in 13.2, I'm just going to erase those to kind of clean things up, right? We need plus a constant. And now that, again, we're doing vector integrals, this constant is a constant vector, right? It doesn't have any t's in it. It's a constant, but it is a vector nonetheless. So if you'd like to, you can write it like this, or you can go ahead and write it as C1, C2, C3, right? Because this is going to have components. Again, all these different constants, but they're different components of this vector here. So either one of these is going to be certainly fine. All right, so I'll go ahead and just leave it like this for the time being. And now we have what v of t is. But again, this is a little bit unsatisfying because really we should be able to solve for c. We want a very specific velocity function. And so in order to do that, we're going to go ahead and use this information up here, right? We know that when you plug in 0, you ought to get out 0, 0, 1. So let's go ahead and do that. So if I plug in 0, so 0, everywhere I see a t, right? It's v of t. So that 0 right there is taking the place of t. So I'll plug in 0 here, plug in 0 there. This one's already 0. These ones are constant. No t's in sight. And again, what I'm supposed to get out when I plug in 0, right? V of 0 is supposed to be 0, 0, 1. And so from this, we can go ahead and solve for our constant vector here, right? We can see that, well, I have 0 right now, and I need to add something to it to get out 0, right? And so, of course, this is just saying that C1 ought to be 0. C1 equals 0. And next up, all right, I have 0 already. I need to add C2 to it and get out 0. So again, C2 happens to be 0 in this case. I know, rather boring. And here's one that's mildly exciting. I have 0. I need to add something to it to get 1, right? Our output, our final result at the end of the day is 1. And so in this case, C3 has to be equal to 1. Now, this is me just like kind of logicking it out. However, you could also do some algebra, right, with our vectors here. You could subtract away 0, 0, 0 from this, right? And of course, on the right-hand side, we'd have this left over. If we subtract away 0, 0, 0, and when you subtract away 0, 0, 0 from any old vector, of course, well, it's just what it is, right? It's 0, 0, 1 still. When you subtract away 0, that doesn't do a whole lot, right? And so, of course, this is exactly what we got from this right here when we were just kind of logicking it out. C1 is 0, C2 is 0, C3 is 1. Okay, from that, we can go ahead and revisit our velocity vector here, v of t, and we can write down a final result. So again, we had all this, and then we were supposed to be plus our C1, C2, C3, right? That constant vector. And now we know this is 0, 0, 1. And so, right, if I was doing web work, it would technically accept it like this. But if I'm imagining, right, if this was maybe a multiple choice question on an exam or a quiz or something like this, maybe this answer doesn't appear, right? But maybe on the other hand, you get t, 2t, and 1, right? And so you do need to know how to simplify these things. Remember, when you add vectors, you just add the components, right? So t plus 0 equals t. 2t plus 0 equals 2t, and 0 plus 1 gives me the 1. So that's where all that's coming from. I'm just adding the components together to add these vectors together, and that's going to be my final result. So I have half the problem down, right? Find the velocity and the position vectors. I have the velocity. Let's play this game essentially one more time here in order to find the position vector. So in order to get position from velocity, again, it's going to be some integral, some antiderivative. So I'm going to be doing the antiderivative of velocity in order to give position. Again, we're doing vector calculus, right? All of these things are vectors here. We now know what our specific velocity is, so I can go ahead and plug this in, t, 2t, 1. And I can take the antiderivative of this. And when I do this, I'm going to get t squared over 2, t squared, t. That is, I'm just integrating component by component, right? Each one individually there. And then plus we get this constant of integration. But again, it's a vector constant. And let me go ahead, I'm just going to leave it like this. I'm going to leave it as c, right? I demoed the other way over here where we actually wrote down the components. Let's go ahead and just leave it like this. And we can see that this also works perfectly fine. All right, but again, this is somewhat unsatisfactory. It's somewhat unsatisfying, right? We want an actual answer out, maybe without these constants, right? And so we need to use this information right here, right? That if you were to plug in 1, then you should get out this vector right here, 1, 2, 0. So the question is, what should those constants be in order to get out 1, 2, 0 when we plug in 1? So let's go ahead and do it. Let's plug in 1. And again, at the end of the day, we want to get out 1, 2, 0 when we plug in 1. So I'm going to do 1 squared over 2, 1 squared, 1 plus this vector here. And just like I brought up last time, right, that we can just do algebra in order to solve this. So let me go ahead and subtract away this vector from both sides. On the right-hand side, we'll just be left with c here. And when I subtract that away, well, let's see, 1 minus a half is going to be 1/2. 2 minus 1 is going to be 1. 0 minus 1 is going to be -1. So I just rearrange that, and now we can see that that is what my vector c is. So now I'm just going to go ahead and plug that in up here. Again, all of this was me solving for the position vector r of t, t squared over 2, t squared, t plus my constant vector, and my constant vector is 1/2, 1, -1. And again, WebWork would accept this right here. So if I was doing this problem on WebWork, this would be perfectly fine to enter in. However, sometimes you just like to clean it up and make it just one nice vector here. Looks very nice. So I'm going to write this as t squared over 2 plus 1/2, t squared plus 1, and t minus 1. That is, I'm just combining each component. The first components make up this, the second components make up this, and the third components make up this. All right, so those right there are my final answers. Here's the position vector. And up here a little bit, this right here was my velocity vector. All right, I hope you guys enjoyed this entire video. Please let me know if you have any questions. You can shoot me an email or just comment in the video or whatnot. And I will talk to you later.